Hello and welcome. I am Neil Walton, and this is a tutorial on learning and information in stochastic networks and queues. I'm at the University of Manchester and also affiliated with the Alan Turing Institute, and it's a joint work with Kwang Zhu at the Graduate School of Business in Stanford. Okay, so what is the aim of this tutorial? Our aim is to provide a summary of the role of learning and information, particularly within queuing theory. And we discuss how we can potentially bridge learning theory with queuing theory so that we can better leverage statistical learning techniques with the theory of queuing systems. Okay. There are some sort of new, quote unquote, new results, but really our intention is to kind of make different connections to provide a review of the area, but we're not attempting to be exhaustive either in that respect. Okay. So queuing systems are really important. They arrive in all sorts of areas of operations research, in communications, manufacturing production systems, supply chain, healthcare. And so they're an important part of the field of operations research. However, it's reasonable to say that there isn't well-established connections between queuing theory and the roles of information, learning, and decision-making, particularly when we compare this, for example, with the area of revenue management, where there is a sort of well-established theory where we can gain information, for example, the context of a customer wanting to buy some goods or services, learning where we might try to estimate, say, the maximum likelihood estimator of some statistics of that context over time, and then we can go about making decisions about, say, how to go about pricing or taking inventory for different stocks and products. And here often, the way to leverage that is to apply some sort of certainty equivalence rule with some confidence interval around it to allow for learning and exploration. However, I'd argue in the case of queuing systems that this is less true. Okay, there are a number of reasons for that, perhaps because of the complexity of the different sets of models is much larger, but also the fact that in, say, a revenue management area, often you imagine a customer comes in, they go, they buy their products, and then they leave. Whereas in the queuing system, you're constantly gaining this inventory, which is influencing other parts of the system forwards in time. Okay, so how are things going to be structured? So the first part of the talk is I'm going to discuss about how some classical learning results, in particular Blackwell's approachability theory, how that can be used to understand a very famous queuing network policy called the MaxWeight scheduling algorithms. So here we're going to be trying to connect together a sort of classical learning theory approach with a very classical queuing scheduling algorithm approach. Okay. And then we're going to build on that a little bit more, and we're going to discuss about how we can use, say, theories of online learning and statistical learning and apply that within some queuing systems, some very simple queuing systems, and see how those theories fit together. Okay, so those are much more kind of examples of how we can use learning results within the context of two queuing examples. Okay, but also we're going to discuss the role of information and queues, and discuss about the importance of less so about learning the statistical characteristics of a queuing system, but more being able to react better to better state determination within queuing systems. Okay. And then finally, we're going to perform a bit of a review on kind of like sort of emerging area, in particular in terms of the application of reinforcement learning theory within queuing theory. Now, as we'll discuss, reinforcement learning in queuing has been around for a long time. And obviously with the growth of reinforcement learning, there's a renewed interest in that from different queuing theories. So we'll review that area. Okay, so we'll start with the examples and then move more towards review and open areas. Okay. Right, so let's start with approachability and the MaxWeight scheduling algorithm. And I'll give a sort of rough structure of what we're going to go for here. So there's this classical result called Blackwell's approachability theorem, which was proven in the 1950s. Okay, and it's about how we can get under adversarial perturbations, get some average to converge towards some convex set here. Okay, so we'll review that in a second. Now, a consequence of Blackwell's approachability is our ability to construct online learning algorithms. So these are algorithms which are irrespective of the set of inputs that need to be learned. It can then learn the best fixed decision. Okay, so this is a very important area of online learning, which also relates to the idea of online convex optimization, and you can go through from the work of Blackwell through to more recent optimizers like the Adagrad optimizer, all within this sort of approachability framework. Okay, and in some sense the two are actually equivalent to one another. So the results of Abernathy, Hazan and Bartlett proving that. Now our aim is to basically say that in fact some of our well-known queuing algorithms such as MaxWeight and back pressure, which I'll describe in a minute, can also be seen as an application of this initial kind of learning result or game theoretic result of Blackwell. Okay, so the point here is to say that actually, some of the reasons that we have these good scheduling algorithms is because we've essentially got good learning algorithms and good learning results over here. Okay, and so that we can see there's a connection between sort of the classical theory of approachability and some classical important results in queuing theory. Okay. Okay, so first let's discuss Blackwell's approachability theorem. Okay, so like I say, it's a classical result in learning and control. It can be thought of as the vector generalization of the Minimax theorem. And so what's the setup here? The idea is that we can make a decision, okay, that belongs to, say, some convex set. Think of the decisions being, say, a set of probabilities that you can choose. And we've got an adversary who can also make decisions. Okay, and again, that belongs to some convex set, and it's probably best to think of that as being on the probability simplex again. Okay, and then based on your decision and the adversary's decision, for each of those, we receive some vector rewards. So we can think of Rij for each I and each j being a vector. Okay, and then we're taking the average of a set of those vectors where the average is over our decisions and the adversary's decisions. Okay, and from that we receive this vector capital R. Okay, and we want to track how well that is doing over time. Okay, and the way we track it is by taking essentially the average reward vector that we get over time. So for each reward over time that we get, we sum those up and take the average to get our average reward. Okay, now notice here we're making a sequence of decisions, both ourselves and the adversary. So we're imagining that given the past rewards and decisions that we've observed, we can then make a new decision. And the same goes for our adversary. Based on the past decisions and rewards received, the adversary can also make decisions. Okay, now the objective we're trying to achieve is to achieve approachability. What does that mean? It means that we've got some set Z. I'm going to assume that Z is a convex set. Okay, and we want to make sure that our average reward gets closer and closer to this convex set wherever it is over time. Okay, so we can think of the adversary potentially pushing us away from this convex set Z, or not, but just essentially making a sequence of decisions. And we're going to try and make decisions that try and get us as close as possible to this set Z. If that's possible, if the average decision can get increasingly close towards this convex set Z, then we say that the set Z is approachable. Okay, and this is regardless of the sequence of decisions made by the adversary. Okay, now if this was all one-dimensional and this set Z was just an interval, then this would be exactly the statement of the Minimax theorem. Okay, that regardless of the actions which are taken by an adversary, you can always find a decision that attains a certain value within our game in a two-person zero-sum game. Okay, all right. So now this is the statement of Blackwell's approachability theorem. Okay, I think it was proven in 1954, I believe, and it states that the following equivalent: that the set Z is approachable if you can choose for every action chosen by the adversary, there's an action that you can choose that sets you inside the set Z. Okay, or even more easily stated, every half space containing Z is approachable. Okay, so what does that mean? Essentially, it means if we take our set Z and we look at the expected change or the expected reward that we get from our decision D of T, if for every A that we decide, if we can choose something that lies inside this half plane, then the set Z is approachable. Okay, so we take our average reward here. We're going to take the projection of that onto the set Z and look at this half space here. If for all A we can choose a decision D such that the expected outcome belongs to this half plane, then we can make sure that we approach Z over time. Okay, so that's the main outcome of the Blackwell's approachability theorem, and it's quite constructive actually, the proof. So once we have this D here, okay, we can essentially construct a sequence of decisions that are going to make us get towards this set Z. All right. Now this can be very useful. It's useful in the context of online learning. Okay, So here's just up here's a picture of what we mean by the online learning setting. So here we imagine that at each time, say t equals 1 here, we can make a decision. Okay, I'm assuming you can decide to go make decision number 1, decision number 2 with some probability d2 up to decision p. Okay, and for each of those decisions you're only going to make one decision, and for that you're going to receive some reward. So if I decide to choose this one here, I'm going to get some reward r of t at this time t equals 1. Okay, and so with some probability I'm going to choose one of these and receive the reward. And we could assume for now that once we've made that decision, we then get information about what all the rewards were. Okay, there are situations when you only get the information from the actual box that you choose, and those are called bandit problems. Okay, now we keep making these decisions over time with the decisions potentially changing. Okay, so if r of t of I is our reward at time t for making decision I, and if we make our decisions with some distribution d, okay, then our expected reward from that decision is just the sum over the i's of the individual rewards. Okay, now the objective in online learning ultimately is trying to maximize your aggregate reward. Okay, so the total reward that you get. So you get a reward at each time, and you're going to sum up these rewards and try and get the best that you can possible. Okay, now often that sort of objective is not completely achievable, and so what one goes for instead is you can't necessarily make the best decision over all possible sums of rewards, but what you can compare to is the best decision compared to one fixed choice. So let's say if I always went here, always chose outcome number 1 here, then you get sort of fairly moderate reward. However, if you see here, the grey squares are a lot thicker. You can see if we chose this last decision all the time, we'd actually end up getting quite a high reward. Okay, so our aim then is to choose a sequence of decisions, okay, whose aggregate reward is as good as the best fixed decision. Okay, so in this case we want to have something that's going to have an aggregate reward which is at least comparable with the sum of all these rewards over here. Okay, now when we do this, we're going to make no statistical assumptions on the sequence of rewards that are made. Okay, and then in this case what we end up doing is comparing the quality of our algorithm in terms of what's called its regret. Okay, so what is the regret? Well, it's the aggregate reward I get from the best fixed decision, and then I compare that with the aggregate reward that I got or expect to get from my algorithm. Okay, so essentially if you have so in this case getting a low regret is good, and getting something where the average, okay, goes down to 0 or grows at order t, then we say it is Hanan consistent, or it has a no regret learning property. Okay, essentially if this is little o of t, then we're able to learn essentially as well as the best fixed choice. Okay, which in some sense is quite a surprising result. It's saying that regardless of whatever happens in terms of these rewards, there's a sequence of decisions that I can make which behave as well as the best fixed choice. Okay, so we're doing at least as well as the best fixed decision. Okay, so that's quite a striking property, and it's, you know, it's surprising that there do exist algorithms which have this ability. And as I'll explain, this is essentially a consequence of the Blackwell approachability result. Okay, so you can show that Blackwell approachability essentially applies that no regret learning results hold. And how does that work? Well, we can think of sort of the vector of regrets that we have. We can compare the average regret of each choice I, or each decision I, compared to our distribution, okay, and look at the difference of those two. Now, we'd be in the kind of Hanan consistent region, or having negative regret if we're in this part of the orthant here. Okay, and what you can notice is for each decision that we make, okay, or for each outcome or adverse reward that we can get, there is always a decision that we can make that takes us inside this set Z. Okay, so if I look at the vector of rewards for each I, there is a decision, in particular choosing the maximizing decision here, which then lands us inside this no regret set. Okay, so if we remember from the Blackwell approachability result, all we needed was that when we project this vector onto our set Z that we want to approach, we need to have a decision that lies on this half of the boundary for every possible reward that we can choose, or every reward outcome that can occur. Okay, and since we can do that, we can also choose this maximizer here to lie us inside the set Z. Then yes, we can indeed approach the set Z, and so we can directly apply the algorithm of Blackwell. It's not necessarily the best of all possible algorithms to choose, but you can choose an algorithm that then means this aggregate reward will converge towards this set Z. So in particular, we have this theorem that says that there's a way of playing, of choosing these decisions D of t, such that no matter what adversarial choice or sets of reward vectors we get, we can have that the average expected regret always tends towards 0. Okay? In other words, we've got a way of identifying a policy which is at least as good as the best fixed choice. Okay? Okay, so far we haven't really spoken much about queuing networks. Here I'm going to describe a model which is called a switched queuing network, and then within that model I'm going to discuss about a specific policy for scheduling called the MaxWeight policy. Okay, so here we have a network of queues with arrivals occurring in discrete time. So we're going to let aj of t be the number of arrivals at qj at time t, and then qj of t is going to be the queue size at time t. Then at each time we can then decide to serve a number of jobs from each queue. Okay, we're going to let S be the set of jobs, the vector of jobs that we can serve from each queue at each unit of time. So specifically in this example, I've represented this in terms of a graph. So here we've got a server at each queue, and I'm drawing a line between two servers to represent the fact that I can't serve two servers simultaneously when they're connected by an edge. So in particular, I couldn't serve this queue and this queue at the same time because there's an edge between them. However, what I've drawn here is a valid schedule where we've got two servers that I've decided to activate and serve, okay, and notice that there's no edge in between them. Okay, so that's one way of representing the set of schedules in a switched queuing network. Okay, and then from that we get a number of departures. I'm going to let dj of t be the number of departures from each qj at time t. Okay, now what I've drawn here is a single hop switch network. That's a model where jobs arrive and then after service depart the network forever. However, it is possible to have a multi-hop version of this, and that's where jobs can be rerouted through the network. Okay, and then relevant to that is a policy called the back pressure policy. Okay, but anyway, we're going to focus on the single hop case and consider the MaxWeight scheduling policy. So what is that? Well, the idea here is we're going to associate a weight with each queue, which is simply the queue length of that queue, and then we're going to multiply that by the number of departures we're going to allocate to that queue, and then sum that up. Okay, and what the MaxWeight policy tries to do is maximize the sum of the weights. Okay, so we try and take the decision rule, which maximizes over the set of schedules the sum of the schedules times the weight. Okay, and that defines the MaxWeight policy. Now, why is that an interesting policy? Well, because it has very good, robust stability properties, okay, which I'll describe now. Okay, so when we have a switched queuing network, like I have one here in this picture, the question is what are the most amount of arrivals or the largest amount of departure rate that I can get from the system. Okay, so this is sometimes called the maximum stability region, the largest set of arrival rates that I can support whilst maintaining vanishing queue sizes. Okay, so in this network here, I've got two queues, and for each queue there's a devoted server. I'm also allowing for there to be a flexible server over here, which can either serve the first queue or move over and serve the second queue. Okay, and then within this I can draw the sets of schedules which I am allowed to do. So notice these grid points here, which I've allowed, give the sets of schedules that we can allocate to the queue. So in particular, the point here, which corresponds to two servers being allocated to the first queue and one server being allocated to the second queue, gives me this point. Or for example, doing nothing would be this point over here. Okay, so once I draw all the schedules in space, If I fill in the area in between, this convex closure here, that is what we define to be, or at least the interior of that we define to be the maximum stability region. So why is that? Well, if I have any arrival rate inside this region here, there's a way that I can construct a departure rate which strictly dominates that. Okay? So for every arrival rate that can occur, there's a way I can construct, if you give me that, there's a way I can construct a departure rate which will then stabilize the system. Okay? So it's the most amount of arrivals that I can support. Though in that model, or in that way I've described that, we need to know the arrival rate in order to make a stabilizing policy. Now the interesting thing about the MaxWeight policy is we don't need to know that arrival rate. So this is a result proven by Tassius and Ephraimides in 1992, and they proved that the MaxWeight policy is stable, okay, so leads to non-growing Q sizes or positive recurrent Q sizes if it's a Markov chain, for all arrival rates which lie in the interior of this set S. Okay, so that's quite striking, as what it's saying is that if there is a policy that can stabilize given the arrival rate, then the MaxWeight policy will also stabilize, but doesn't need to know the arrival rate to the Q's. Okay, now that should invoke a lot of thoughts of the Blackwell approachability theorem that we've just described, that regardless of what the adversarial decisions are, I can make a decision, a policy decision myself, or a sequence of policy decisions which lead to a good performance or good Q sizes in this case. Okay, so one of the things we discuss in the tutorial, in the article, is how essentially this sort of famous result about the stability of queuing networks can be seen as an example of Blackwell's approachability theorem. Okay, so how do we do that? Here it is in a picture. So we can see that approachability in Blackwell approachability implies MaxWeight stability properties. That is because we can think of the Q size as being the sum of the arrival decisions minus the departure decisions that we've made, where we think of the arrival decisions made by the adversary and the scheduling decisions made by us as a player. Okay. Now our task in trying to minimize Q sizes is to get the average Q size vector to approach this set here, the negative orthant again, a bit like in the online learning example from earlier. Okay. Now in this specific case, the change in this Q size vector is going to be given by the average arrivals decided at time t minus the departures vector that we decided ourselves. Okay. And remember that approachability holds if, when we project our point onto the set Z, if we can always make a decision that lies on the left-hand side of this half plane, or on the side of the half plane containing Z. Now notice, this is always going to hold for the case of this vector. And why is that? Well, because the distance from the arrivals minus the departures to this half plane over here is exactly equal to the MaxWeight decision here minus the Q sizes dot producted with the arrival rates. So since we're taking the MaxWeight decision, we get this maximum over here minus this arrival rate, and since this belongs to the interior of our stability set S, this is definitely going to be bigger than this, and so we're always, this is always positive, and so we're always on this side of the half plane. Okay. So essentially what we prove is the MaxWeight policy in itself is really an instance of Blackwell's policy, and as a consequence of the Blackwell approachability theorem, we can show that for any subcritical arrival rates which lie strictly in the interior of this set S, then we get sort of Q sizes which go to 0. Okay, so I find that quite interesting that there's this sort of very strong link between Blackwell approachability and online learning theory, but actually one of the kind of classical policies and algorithms in queuing theory can also be seen as a consequence of that original Blackwell result. Okay. So you can argue that the reason that MaxWeight and also the black pressure algorithm as an extension is robust over a wide range of arrival rates, including those chosen adversarially, because it's a special case of Blackwell's approachability theorem. Okay? So in some sense we can think of the reason we don't need to know these arrival rates for MaxWeight is because it can be interpreted somehow as a sequential learning algorithm for the vector of arrival rates that are coming into the queuing system. Okay? So just as classical results in online learning can be seen as a consequence of Blackwell approachability, we also see that classical algorithms in queuing can also be viewed as a consequence of Blackwell's approachability theory. Okay, so that's great because we can see that there's a connection between adversarial learning and adversarial learning in queuing as well. Okay, so we're going to now having built up that connection, we can then extend this and begin to think about the consequences in terms of service decisions as well. Okay, so that's what we're going to talk about next. So we saw for MaxWeight that stability is achievable with an unknown arrival rate. However, the same isn't true for service rate. So if we don't know the actual how much service we're going to get per unit time, then we don't have these same robust stability properties. So one of the interesting things to look into next is how we can still use online learning in order to learn service rates and what impact that can have in terms of the queue size. So what I'm going to consider here is a reasonably simple kind of framework where we can consider results in online learning and regrets, which we discussed earlier, and we can ask those questions in terms of the queuing system. Okay, so recall from before that an online learning setting was something where we have to make decisions. Okay, so we've got sort of decision 1, 2, up to the last decision, maybe decision P. Okay, and at each time we can choose one of those decisions and we receive some reward given by the sort of amount of grey here. Okay, and we're looking at how the sum of the rewards that a policy makes over time compares with the reward from, say, the best policy. Okay, and we can present this in the terms of a queuing system. An easy way to do this is just to simply take this picture and turn it by 90 degrees and call it a queuing system. So if we do that, we end up with this model over here. We can imagine that there's a server, and the server can decide different service modes. So it decides, is it going to try and serve this first job under service mode 1, 2, or 3, up to any number that you like. Okay, so each of these are different ways we can think of that the server might treat service of that customer. And so what we can ask is, how does the regret of the online learning algorithm affect the regret and the queue size of the queuing system? Okay. So in particular, I'm going to phrase things as follows. Instead of thinking of things as rewards, we're going to think in terms of times, okay, the amount of time it takes to serve a job. Okay, so what we can say is we're going to let tau m of t be the time that it takes to serve job T under service mode M. We're going to let T star be the optimal service. So for now, we're going to assume there's an optimal service. Actually, in the original paper that we wrote on this, we didn't do it this way. But for this setting, it's quite simple to do it this way. And we're going to let pi be our policy that each time is going to choose a service mode for each job as it arrives. Okay. And here, the regret is the sum of the services, the service times, minus the service time we would have got if we'd chosen the optimal service mode. Okay. Now, that gives us sort of a setting in terms of online learning. Now let's consider an important result in terms of queuing, which is Lindley's recursion. Okay, we can get a view of what the workload is at a queue in terms of this iterative recursion. So the workload at time t under policy pi is the maximum of either 0 or the previous workload plus the time it took to serve the job there minus the inter-arrival time, the time between the arrivals of jobs. Okay, so the kind of service workload of a single server queue under this policy pi can be given through this Lindley recursion here. Okay, what you can show by analysing that Lindley recursion and expanding it out, we end up with some sums in terms of the queue sizes. Okay, and what you can show is that if t0 is the last time that the queue is empty, i.e. under the policy pi, wt of 0 is equal to 0, then the difference of the workload under the policy pi compared to the workload under the optimal policy is bounded essentially by the difference in the regret. Okay, the difference in the regret at time t compared to time t0. Okay, we can use this as a kind of meta result that if the regret is sublinear, okay, so we've got Hannon consistency or no regret learning, then we can, and also if this optimal policy wt0 is stable, as in it doesn't grow linearly in time, then we can also argue that any policy that's no regret learning policy is also going to be stable. Okay, so what we can say is that the ability to construct an online learning algorithm then means that we can come up with a service rule that's able to stabilize the system. So again, making this connection between the online learning and the stability of the system. Okay, so if a good service rule exists, again we see that a good learning algorithm will be able to stabilize the system. Okay. You can use this more specifically. In particular, if we know that the system is stable as in it empties quite frequently, that is meaning that at time t, the time since it was last empty is order 1. So think of finite renewal times as emptying quite frequently. And if you have an algorithm with a regret, which is logarithmic in t, which you often see for statistical problems, where the IID say service times, then this bound above is going to be approximately sort of log t minus log t naught minus 1. Okay. So then we can see that the difference between the optimal policy and the policy that we choose is going to be about order 1 over t in time. Okay. And this is just using the lemma before, we can sort of recover essentially a result very similar by Chris Sami and Sanjay Sakatoya and co-authors. Okay. Now, one good example where we can kind of see how this framework and the lemma from earlier can be used. So let's consider a queue with contextual jobs. Okay, so here, let's imagine that we've got a single server queue. At each time, a job arrives and it's got some context X. So that's, say, information about the job that's arrived. You could imagine the customer's filled in some form, or we've got some data about the nature of that job. And then based on that, we can decide how we're going to go about serving the job. Okay. So let's suppose each job has a context here, which is some vector in RD. And then let's suppose there's also some response. So after we serve the job, we can determine if it was a plus type job or a minus type job. Okay, so assuming there's 2 service modes here, and if we chose service mode correctly, then we'll get a fast service. Okay, and if we chose it incorrectly, then we get a slow service. Okay, so here our policy. If our policy, given the context, correctly identifies the response here, then we get fast service. If we're incorrect, then we get slow service. And we're going to assume a specific type of policy. We're going to assume the policy takes our context feature map and then applies a parameter to it, the dot product here. Okay, and if the dot product is positive, then we say it's a positive +1 policy, and if it's negative, we say it's a -1 negative policy. Okay, right. So in this, we're trying to basically learn the features of the jobs in order to determine which of the 2 service modes we use. We could use more than 1 service mode, but it's simpler in this case for just 2. Okay. So this is a way that we can fit in the results previously with quite well-known learning algorithms. In particular, there's an algorithm known as the perceptron algorithm, okay, which can essentially choose what these weight vectors are. So here we think of space being an RD for our context, and we're essentially labeling pluses and minuses in this space. And we're trying to find a half plane that essentially divides up the pluses from the minuses. So we can see here, this will be a slightly better one than the current one presented here in green. Okay. And if we apply a gradient descent to a specific objective, we end up with what's called the perceptron algorithm, okay, which is just given by this rule over here. Okay, we can use some bounds from online learning, in particular online convex optimization, to prove the following famous result, which is called the perceptron mistake bound, which goes back to the sort of, I think, 1960s, Novikov and people like this. Okay. Which is, anyway, the result that's proved there is that if there exists some optimal W star which separates out the decisions, the labels of the responses, from the decision of the policy, okay, by some fixed amount 1, then the perceptron algorithm will eventually figure it out. The number of mistakes made by the perceptron algorithm is going to be bounded above by some constant. Okay, so there we can directly use online learning results in order to prove that the number of mistakes made by this algorithm in terms of labeling the customers as fast or slow jobs is finite. Okay. So what we get then as a corollary of our result in terms of these waiting times is that if we apply the perceptron algorithm to this contextual queuing model, then the waiting time of customers is also going to be within a constant factor of the optimal policy. And indeed, from the way that lemma was proven, we can show that if we look at the last time that the queue was 0, the last time that under the policy we emptied the queue, as long as it's after this time d, then we're going to exactly follow the optimal policy from that point onwards. Okay, so this shows that we can use our kind of regret bounds and how they worked in terms of a queuing system to give direct results about the performance of a queuing system when we're applying a kind of learning algorithm with contextual jobs. And we show that we eventually learn the correct optimal policy in this case. In reality, most models might be stochastic, or there might be some margin of error that occurs at all moments in time. And so there are results like for the perceptron algorithm where we have kind of interchange arguments, where we don't get a tight enough bound to say finite number of errors, but you can put tail bounds and etc. on the number of errors, and those would in turn transfer over to the queuing system as well. Okay, but it's particularly simple in this case of the perceptron algorithm, which again is a classic result in learning theory. We can see there again that we can take models from learning theory and begin to place them in the context of queuing systems. Okay, so far we've seen that certain classical queuing policies like MaxWeight, because they can be interpreted as an adversarial learning algorithm, they're robust to a wide range of arrival rates. However, when we look at service rates, the same isn't true. It seems that we need to be able to learn those service rates. Okay. So, however, we can use bounds and essentially a kind of perturbation analysis to show how the performance of a learning algorithm can have impacts on the performance of a queuing system. Okay. Now, a question over this is, what information should we learn, and how does this information affect performance? So we've looked at arrival rates and service rates, but what is the correct thing to try and learn about the queuing system? Now here we'll begin to move away from kind of examples to more of a kind of high-level discussion about what seems to have worked in other systems and what other authors have looked at in order to answer these types of questions. Okay, so now we're going to discuss the question of information and queues. So one thing that we follow in our discussion in an article is follows from this paper of Liu et al. On reinforcement learning bit by bit. So a useful taxonomy to think about any system really that you want to perform learning on and decision making on is to separate out the kind of decisions the kind of information you want to learn about the system into two settings. One is epistemic information, which is essentially uncertainty about the model that you're considering and its parameters, or aleatoric information, which corresponds to uncertainty about the state of the model at a particular moment in time. Okay. And what we're going to discuss really is in the situation of queuing systems, it seems that having better aleatoric information can have a much bigger impact on performance than trying to learn, say, the underlying service parameters of the system. Okay, so just as before we were discussing about service rules, I'd argue that if you can gain state information about a queuing system, that's going to have a more pronounced impact on performance. And we can do this discussion in terms of some examples from prior work. Okay. So an example from Stidman, but then is expanded by Spencer et al. In 2014, and Quang is one of the co-authors on that paper, my co-author here, considers the following admission control problem. You have a single server queue with some arrival rate lambda, okay, and you can decide either to serve or divert some proportion p of the traffic, okay, or some amount of the traffic, okay. And then in turn give that a slightly slower service rate. Now this is a classic model of admission control, where if the system can become unstable, you need to make decisions in order to redirect jobs in order to get the optimal control on the system. Okay. So then the question about that becomes is, what is the optimal decision in order to minimize queue lengths when there's a objective where you have to minimize costs of holding jobs, but also try to get the most service out of the system. And what Stidman shows in 1985 is essentially characterizes the optimal policy as a kind of threshold policy, and shows that under that rule, as we get lambda and that get closer and closer to 1 minus p, our service rate over here, that the optimal queue length in that system for admission control is going to satisfy an asymptotic where it's approximately log of 1 minus lambda. Okay. Now, that seems like the best we can do under a certain characterization of the model. However, if you're given just a small amount of future information, so suppose we've got this Poisson process of arrivals, and we're told some information about the number of arrivals to occur over the next L, capital L, time steps. Okay? If that happens, there's quite a different policy that becomes now the optimal policy. We don't just have the information about the queue size and the service rates, but we also have this additional information of the state of the Poisson arrival process. In that case, we find that beyond some threshold L, you can keep the expected queue length now constant as lambda gets close to 1 minus p. Okay. On the other hand, below some threshold, if that look-ahead window L is below that kind of log 1 minus lambda threshold, then we go back to the kind of Stidman result and get that kind of asymptotic. So what we see is this kind of sharp transition where if we've got enough information about the system in terms of not just the queue size and the parameters, but also about the number of arrivals that are going to occur over the next L time steps, they can have a very big impact in terms of the queue size of the system. Okay. This is also a phenomenon that can happen in load balancing as well, where just getting a little bit more state information about the system can have a much bigger impact on the optimal policy rather than learning, say, the average performance of the system or the average parameters. Okay. So another example is a paper of Germanik et al. In 2018. They're considering a load balancing model where jobs can arrive into the system and arrive at a dispatcher. Now the dispatcher on an arriving job instantaneously has to make a decision about which servers to send the job to. Okay. And in this model, they consider a setting where the servers can talk to the dispatcher sending a number of bits per unit time when they're idle. Okay. There's a rate of messaging from the servers back to the dispatcher in order to help with these decisions, and also the dispatcher has a memory of it can remember a certain amount of information about which servers have communicated with it. Okay. And again, we can get quite a complex relationship between, say, the message rate and the memory in bits. If there's not enough messages and not enough memory, then we end up with positive delay in the system. Okay, so the jobs end up waiting in order to receive service in the system. However, we see that there's a certain threshold where above that threshold, we end up with a system with essentially zero delay. Okay, so again, we see by storing sufficient amount of state information, we can then improve and get much smaller queue sizes than in a regime where we have insufficient information and essentially working on average parameters. So I'd say in queuing systems, it's not just a case that we need to be learning statistics and looking at those as a perturbation of the original queuing system, but we also need to be thinking about what's the correct state description in order to come up with an optimal rule. And other examples of this exist as well. So for example, we can consider dynamic alternative routing, which occurs in telephony networks, more in the 80s and 90s. That if we want to make a communication between A and B, we can then make a direct communication by taking up some capacity in one of these circuits. However, if all the circuits are full, then one can try to do a dynamic alternative by being rerouting that job. Now, if you look at how AT&T used to do this in the 90s, they used to collect information about the average loads on all the different links and then provide, after determining the arrivals and services required, they do an optimization to determine the amount of routing that need to happen on each trunk of this network. However, what was found in alternative work is that if we directly use the information of a loss, so when we try to make a direct call, if we cannot do it, then we reroute, then you can gain substantial benefits compared to the offline optimization. So rather than estimating arrivals and services and then going about performing an optimization, just directly reacting to current state information and responses led to much more improved telephone routing service. Okay, the same holds with switch networks. So as we had our example earlier of this flexible server, if we had our arrival rate somewhere in the middle, then we'd know that the flexible server to do the optimal thing would to spend 50% of its time here and 50% of its time here. Okay, if we looked at a randomized policy, which would the flexible server would then jockey at random between these two queues, that would lead to one queue length. However, if we looked at the alternative system where the server reacts to the current state of the queues, if it knows that the current queue that it's at is idle, it moves on to the second queue. And that's going to have a much lower queue size than the static system. So even if we learn the arrival rate parameters and the service rate parameters, actually using current state information can lead to a much better queue size and much better performing system. Okay. So what we see there, as these sort of examples seem to suggest, is that to gain good aleatoric state description and then optimize given the current state is much better than to statistically estimate epistemic parameters and then optimize the average performance. Okay, so rather than taking the average system and optimizing average service to those parameters, you're going to be doing much better by thinking about what the state description of the system is overall. Okay, And also we see in more recent work, in the two more recent cases, that there seems to be this kind of threshold between a good and a bad state description, that there's a very sharp transition from having sufficient information to come up with really low Q sizes and really good performance, and a bad system which essentially behaves as good as average. Okay. All right. So that's kind of a high-level discussion on the role of information in terms of making decisions. Okay. Now let's move on to kind of more current topics in terms of the use of information and learning, and in particular reinforcement learning in the context of queuing systems. Okay. The reinforcement learning problem is, very briefly, and like I say, it's a big field with textbooks and conferences and all the rest of it. Here we have a problem. We have what we say is an agent, so some sort of algorithm or decision maker, and at each time the agent can make some actions which are decisions, and those interact with an environment. In this case, we're thinking of it being a queuing system. Now, those actions influence the state of the system, and from that the agent is fed back some information about the state of the system and also some rewards. Okay, and through observing this sequence of states and rewards, the agent will choose actions with the objective of maximizing the sum of the rewards that it receives, perhaps the discounted sum of the rewards that it receives. Now, if the evolution of the state feedback is a Markov chain in terms of the state and action taken, and also if the reward is, then the problem of maximizing the sum of the rewards is called a Markov decision process. And usually the type of policy that maximizes this is a direct function of the state. So we take the state, and as a function of that we choose the action, and if we choose that state in a specific way, in particular so that it satisfies this equation here, which is known as the Bellman equation, then that policy should be optimal for the problem. Okay, so that's the theory of Markov decision processes in a nutshell. However, if the model is not known, in particular if this matrix P is not known, or is not sufficient to yield the process as a Markov decision process, and similarly if the reward function here is not known, then we have to try and learn essentially this Bellman equation fixed point approximation. And one way to do that is through doing a stochastic approximation procedure. So here we're trying to search for this fixed point, determine the square brackets to be equal to 0. And so if we update in this way, we hope to find a fixed point which satisfies the solution of the Bellman equation. Now this is an algorithm called Q-learning. However, often this involves storing information, a variable for every state and action within the system, okay, which is often not feasible. So in that case, what we can do is replace this Q function here with some function approximation, perhaps a linear approximation like we had earlier, okay? And we can do a similar update which tries to get this fixed point as well, okay? And that's some, if we use a neural network for this and a few more tricks, this is sometimes called like the DQN procedure, okay? Now, I want to make a point that queuing has quite a good history in terms of the development of reinforcement learning, particularly when we look at more modern methods that use neural networks. So, you know, the sort of breakthrough paper that considered neural networks in the context of gameplay is this TD Gammon algorithm by Trejaro in the 1992. And we get this not long after, I think it's Crites and Bartow, 1996, which looks at how we can leverage that neural network approach to reinforcement learning in order to optimize a network of queues, which are meant to model elevators. Okay. We also have key contributors such as Bertzikas and John Sitsiklis. Obviously has worked a lot extensively on the MaxWeight algorithm, which we discussed earlier, and also kind of wrote the first book really covering these kind of dynamic programming techniques using neural networks, which are now very important to reinforcement learning. Okay, we also see applications fairly early on with Zhang and Dieterich to job shop scheduling problems, so the idea of how we assign tasks to different resources to solve scheduling environments, and then Singh and Bertzikas looking at dynamic channel allocation. Finally, also we see one of the first papers on using the cross-entropy method in order to do a policy search algorithm. They consider the example of inventory control in that paper. Okay, so a lot of the kind of early algorithms which were developed are quite quickly passed over into the case of queuing systems. And I think that kind of remains to some extent true today. Okay, so if you can apply a reinforcement learning algorithm, then there's a good chance it's going to work with a queuing system, as we'll discuss in a second. Okay. However, there are a lot of challenges in applying reinforcement learning techniques to queuing theory, And here's just a list of a few of the things that have been highlighted in other papers which we'll review shortly, that are issues between making a reinforcement learning theory work for queuing theory. So the first thing is most results in RL assume a finite state space where every state is visited some fixed proportion of the time under sort of every policy. Now that's not very realistic in the case of queuing theory. So we tend to have, in queuing models, tend to have a very unbounded state space. Also the cases that we care about are things like how big the queue is, and so if the cost is the queue size, that can also be unbounded. Okay. Then, given that, we can also care about the case where the loads are quite big, which also then leads to further exacerbates the problem of these costs and the unbounded state spaces. Further, even if we do solve the MDP problem associated with the queuing network, it's not necessarily true that that has to give any sort of guarantees in terms of the stability of the system. We might not have stability guarantees like we did for the MaxWeight algorithm, which was robust across a wide range of loads. Other points have been noted by people as, for example, issues with non-stationarity, that things might change over time. Queuing systems often tend to be quite distributed. So, for example, most importantly, communication systems, we need algorithms which are going to be highly decentralized and be able to run independently of one another. So decentralized coordination is a big important issue there. Often, reinforcement learning algorithms are going to be trained through simulation, particularly neural network type models. And so there's always going to be this issue of when we pass over a simulation model over to a real system, whether that's going to replicate that behavior in real life. Okay. Other perhaps slightly less critical issues are things like continuous time modeling, and also but is quite important, is incomplete state information. So particularly in these kind of very distributed, decentralized problems, we're only going to get local information in order to make our decisions. Okay, and so understanding the theory of those is quite important. Okay. So this summer, Nicholas Gass, Mengdi Wang and myself organised a workshop at the Sigmetrics conference on reinforcement learning queuing systems, and so this is just a quick discussion of the kind of papers and topics that that came up in that workshop. So we have a number of works, particularly this one by Deveret Shahar, Zhao Minji and Zhu, who look at the infinite state space setting and show that we can do reinforcement learning in infinite state space settings, provided we've got a Lyapunov function that's essentially we can learn and provide stability to us. Okay, a similar kind of paper to this also notes that we can learn an RL policy that is optimal, provided we learn it on some truncated state space and then apply a different mechanism to stabilize outside of it. Okay. We're also seeing efforts to tackle the sort of decentralization issue. A very fine paper here by Ku, Wyman and Lee. Look at decentralized coordination, not necessarily just in queuing systems, but they essentially show that if each agent in a network operates based on local information, then you can always be within a constant factor of the optimum. Okay. Jim Dye and Glusman have this very fine work recently, which essentially looks at how we can apply policy gradient algorithms, so a certain type of algorithm for optimizing reinforcement learning problem, how we can deal with these large variance considerations, high costs, wanting to do average programming rather than discounted programming, and look into the different tricks that we can apply to those to make them work better for queuing systems. Another related paper that's not really reinforcement learning but fits very much into that way of thinking is this paper of Dika, Ghosh and Squalante, where they essentially look at how we can apply queuing formulas to improve gradient updates when we're trying to do some optimization on a queuing system. I think it's a very interesting angle for future investigation. We haven't seen a great deal of follow-up work on that paper. Also, there's a nice paper here, Zaki, Mohan, Goplan and Manna, who've been looking at how we can apply bandit algorithms within a queuing context so that we have a different bandit algorithm we can apply within different states of a queuing system to come up with a good control procedure. And then finally, we're also seeing that for systems where we do have a closed form solution, for example, in inventory control, how we can then use regret bounds in terms of the learning system in order to get an understanding of the behavior of the optimal control, the regret with respect to the optimal control when parameters are unknown. It's a little bit similar to the analysis earlier. Okay. So although there's progress towards making this sort of the theory of reinforcement learning match up with the theory of queuing, in recent literature. I would say that there's nothing to stop you applying a reinforcement learning algorithm directly to a queuing system. So here's a brief study that we did at the Turing Institute, where we looked at a road traffic simulator. Here we've got a commercial road traffic simulator called VISIM, and what we did is we compared a neural network learning architecture here. So here DDQN doesn't stand for data-driven queuing network, but stands for double deep queue learning network. Okay, we compared the performance of a trained algorithm under this reinforcement learning algorithm to the performance of Mover, which is a commercially available traffic signal control system used throughout the UK. And what we found with a relatively small amount of training, we could come up with a policy that significantly outperforms current commercial systems. Okay, and I think that kind of sums up where learning should be coming in within queuing systems. We shouldn't be using learning to replace modeling as such, but learning should be accounting for the parts of the system that we can't model well. So for example, in a road traffic situation, we can't really model well the arrival and the speed up and the slow down of cars. Okay, we can come up with a good model of how much service we get, or maybe what the arrival rate is, or what is a good policy like MaxWeight, but we can't capture these kind of other additional features well. And so given that, we want systems that are able to learn those aspects of the system while still accounting for the kind of good macro level algorithms that we know work. Okay. Important things that are happening at the moment in terms of reinforcement learning in queuing. We're beginning to see an increasing number of applications. So we have Dai and Chi looking at patient inflows. We've had a lot of work from Holland by Rob van der Meij and his team looking into emergency response. Okay, so ambulance placement. Like I say, there have been works on road traffic, and at the Turing we're very interested in that, and been talking with some companies in London and the south of England about that. Have papers by Ku on manufacturing and looking to reinforcement learning there, and also a number of very recent works on data centers, including from DeepMind, as well as early work from Trajaro, which look into the application of reinforcement learning for data center assignment and congestion control. Okay, like I say, often these reinforcement learning algorithms are trained through simulation, and so this is one of the kind of bottlenecks that we have at the moment, kind of a lack of simulators. So Jaminji, Sid Banerjee have been looking into developing a suite, a sort of software package called OR Suite, where we can kind of test out algorithms on kind of contemporary operations research models. So I think that's a very interesting initiative and very supportive of that. Also for specific applications, we have kind of commercial grade simulators like the NS3 simulator for internet modeling, the SimGrid simulator for high performance computing, and then also VISIM, Sumo, and AIMSUM. And we saw VISIM earlier as a commercial road traffic simulator. And I think one of the interesting things about the way that reinforcement learning problem is approached is that people tend to try out problems, take it as a kind of exploratory research problem, and then try to develop algorithms and solutions. So I think more work on application-driven and simulation-driven solutions might lead to very interesting research and problem areas in the theoretical queuing theory research, as well as reinforcement learning research. Okay, so I certainly think our community could benefit a lot from that. Okay, and finally, to conclude, so let's discuss what we've covered. So first we talked about a classical result used in online learning called Blackwell's Approachability Theorem, and we saw how Blackwell approachability in fact implies the stability of a famous queuing policy called MaxWeight. Now this potentially has implications in terms of reinforcement learning and other areas. If we want to have a robust agent, then we should think about the arrival process undergoing some sort of adversarial training. So we want to have adversarial arrivals in order to get a good robust policy. We also saw how sequential learning could fit quite naturally with the learning of service within a queuing system. We showed for a fairly simple queuing system how we could apply the regret analysis, for example, of the perceptron algorithm in order to imply bounds on the queue size and closeness to the optimal policy for that queuing system. We then kind of stepped back from learning arrivals and learning services as we began to think about, well, actually, do we really want to be learning the state of a queuing system? It's more, and we saw from examples of prior literature that often by increasing state information, we can design more effective policies than we can from trying to estimate parameters and trying to optimize the stationary system under that policy. Okay. Finally, we talked about the kind of emerging area of reinforcement learning within queuing, and maybe emerging is not fair because queuing applications have been applied to reinforcement learning, or it has been an application area of reinforcement learning for quite a long time. Okay, however, it's also reasonable to say that although there is emerging work, there's still a lot of work to do in order to merge the theory of reinforcement learning with the theory of queuing. And as we saw towards the end, we can see that that doesn't stop us from applying reinforcement learning algorithms to queuing systems and come up with successful policies, at least empirically. And so we think the community could benefit a lot from more exploratory research into different simulators of queuing systems and trying out different policies and learning algorithms in order to optimize them. Okay. So, and last of all, thank you for listening and for coming along to this tutorial. And there's a paper associated with that in this year's tutorial series. Thank you.